So what I'm going to do really quick is spend some time talking about these equations and some of the variables that make it up. The first equation on our list is A is equal to C. It seems kind of a stupid idea, but it's actually really critical to understand what exactly that means. If you don't understand this, then you don't understand when I can use those equations. The idea of A is equal to C means that the acceleration of that object, whatever object you're observing, has a constant acceleration. That means that its velocity is constantly changing by the same value for the entire motion you're observing. Okay, there are certain problems in which we're going to have a changing acceleration. If we experience that, then we can only use these equations in those zones where the accelerations are constant. Okay, car moves with a constant acceleration, and then right here it applies the brakes, and here. So that means that I can use these equations, but I can only move where the car is moving, and then cut another set of equations to describe when the car is applying its brakes. So we have to remember that this is my stipulation. I can only use these equations if this is true. And if it is not true, we need to find areas and regions where it is true. So those true areas, those areas where this is true, we can use those equations to describe what's going on. Okay? So first equation, it seems very basic. It's not really an equation if you want to think about it that way. But the idea is that the acceleration of that object is constant. Or the acceleration of that object is constant within regions. Okay? So that's the first equation we're going to talk about. The second equation we're going to talk about is this velocity final is equal to initial velocity plus acceleration times time. This equation is describing what the object's final velocity is going to be. We're looking to see how fast it's moving at the end, v final. And the things that affect what its final velocity is are the initial velocity, how fast it's originally traveling when time stops. Well, not when the time stops, when it starts. How fast the car is originally traveling when the time starts. And then this additional term of acceleration and time. Let me make that plus sign a little more visible. Okay? So, final velocity is dependent on the initial velocity and this acceleration times time, which is nothing more than how much the velocity changes by. The change in velocity per unit of time times time tells me how much my velocity changes by. Okay? So final velocity is dependent on those two terms. That's what that equation is trying to tell you. Final velocity, initial velocity, acceleration, time. Okay? That's the second equation. The third equation that we're talking about is talking about this distance. And I'm talking about the x in this case, but there's no reason not to talk about the y, the z, or the r. It's talking about distance. And it's saying that the final distance, or not distance, displacement, if you will, or more appropriately, position. The final position of that object is dependent on its initial position, this xi, and then these two terms are a discussion of how much that position is changing. Okay? If you look at it, v initial times time is the initial rate in which position is changing per unit of time times time. This is the initial change in the position depending on the velocity. Okay? This second term, this 1/2 at squared, is the rate in which this velocity is changing and how much that change in velocity is going to affect the final position. It's a huge rate of change, then we can say that this is going to have a huge effect on that final position. Because it's kind of a little more complicated. It's the rate in which velocity is changing, which we find out that velocity can change the position of an object. So the rate in which it changes and how much effect that rate has on it. That's where these terms are coming from. Okay? This is just saying how much does the rate of change of velocity affect its final position. Okay? That's the third equation. The last equation, I'm just going to go straight into it. 2 times the acceleration times the displacement. Now, you can see it in different forms but this is probably the form you're going to be most familiar with. Okay? 2 times the acceleration times the change in the object's position is equal to v final squared minus v initial squared. Now, there is really no simple way of describing it. There is when we talk about energy, there's a simple way of describing it. It's just relating all the variables to each other without having to concern ourselves with time. Once again, a time-independent kinematic equation. Those are the 4 equations you need to know in order to solve a kinematic equation. Okay? The next group of videos that I'm going to go over are solutions using the kinematic equation. Okay?